Okay. In the previous lecture, we talked about adjacency matrices and also incidence matrices. For incidence matrices, we talked about this example, which is about undirected graph. Here, we have created the incidence matrix for this undirected graph. Now we have another example. We are given a directed graph. We need to create the incidence matrix for this graph. We say we create the matrix like this. First, we write down the columns, the rows here. These are the vertices. This is A, B, C, D, and E. These are the vertices. And also the edges are E1, E2, E3, E4, up to E6. Okay, we have this matrix. We create this matrix. We say for the directed graph, as you see, here we have arrows. We have arrows. For the directed graph, for A, for vertex A, if E1 connected to E2, to A, if E1 connected to A, as you see, this is E1 as connected to A. We have two cases, if it's outgoing or incoming. Okay, if it's outgoing, we say it's 1. We just write down 1 here. If it's incoming, we write down -1. But if it's neither incoming nor outgoing, we write down 0. Okay, look for vertex A. For vertex A, as you see, for vertex A, we have this which is outgoing, and this which is outgoing, and this one is incoming. Here, these are E1, E2, and E3. The edges which are connected to A are E1, E2, and E3. 2 of them are outgoing arrows, and one of them is incoming arrow. So the incoming arrow, for the incoming arrow, we write down -1. For the outgoing ones, we write down 1. Okay, as you see, for E1, for A, for vertex A, for E1, we write down 1. For E2, we write down 1. Why? Because these 2 arrows are outgoing arrows from A. And we write down -1 for E3. For E3, we write down -1 because it's incoming arrow for A. And for the rest of the edges, we write down 0 because others are not connected to A. E6, E4, E7, E5, and E8. These are not connected to A. That's why we write down 0 for them. As you see, for E4, E5, E6, E7, and E8, we write down 0 for row A, for vertex A. Then for vertex B, the arrows which are connected to B are E1, E4, and E6. For only these 3 edges, we write down, we don't write down 0. For others are 0. Here, for E2, E3, E5, E8, and E7. For these edges, we write down 0 for B, for vertex B. As you see, for E2, since E2 is not connected to B, we write down 0. For E3 is 0. E5 is 0. E7 and E8 are both 0. But for those which are connected to B, are E1, E4, and E6. How about E1? E1 is an incoming arrow. We write down -1 for E1. For E4, it's outgoing, and E6 is outgoing. We write down 1 for these two. For the outgoing edges, we write down 1. For the incoming, we write down -1. And for others which are not connected to that vertex, we write down 0. Here, for E1, we write down -1 because it's an incoming arrow regarding. And E6 and E4 are outgoing arrows from B. They are outgoing arrows from B. We write down 1 for E4 and E6. This is E4 and this is E6. Look. And this also. We write down for these two. For the only connected arrows to the vertex, we don't write down 0. Okay? And you have two cases for the connected arrows. It's either incoming arrow or outgoing arrow. If it's incoming arrow, we write down -1. For outgoing arrows, we write down 1. Then for for vertex C, we have only 2 arrows which are connected to C, which are E2 and E5. E2 is an incoming arrow. E2 is an incoming arrow. So we write down -1 for E2. For C, E2, we write down -1. And for E5, it's outgoing arrow. E5 is an outgoing arrow from C. Write down 1 for E5. This is E5. We write down 1. And for the rest of edges, we write down 0 because others are not connected to C. Then for D, we say here we have 1, 2, 3, 4, 5 arrows. 5 arrows are connected to D. 5 arrows are connected to D. For the loops, we write down 1. That's written above here. We say if it's a loop or outgoing arrow, we write down 1. If it's incoming arrow, we write down -1. And if it's not connected, we write down 0. Here, the edges which are connected to D are E3, E4, E5, E7, and E8. E3, E4, E5, E7, and E8. You have these 5 edges which are connected to D. Which of these is an outgoing arrow? Which of these is an outgoing arrow? We count this as an outgoing arrow. This is also, and this also. Here you have 3 outgoing arrows. For these 3 outgoing arrows, we write down 1. And you have 2 incoming arrows, which are E4 and E5. We write down -1 for these 2. And for the rest of the edges, we write down 0. Yet for D, we have 2 outgoing arrows, which are E4 and E3. For these 2, which are E3 and E7. We have these 2 outgoing arrows. We write down -1 for these 2. For E3 and E7, we write down -1. This E3, I confused. We write down 1 for this, not -1. For only the outgoing arrows, we write down 1. We have E3 and E7. For these 2, we write down 1. E3, this is D, we write down. And E7, this is D, we write down. And we have given that for the loops, we write down 1 also. For the loops, E8 is a loop at D. So we write down 1 for E8 also. We have only 3 ones, which are for E3, E7, and E8. And we have 2 negative ones, which are E4 and E5. At E4 and E5, we write down -1. For D, For E4, it's -1. And for E5, we have -1. Okay? Except those which are connected to D. We have E1, E2, and E6, which are not connected to D. We write down 0 for them because they are not connected to D. Okay? And then for E, this is vertex E. For vertex E, we have only 2 edges which are connected to E, which are E6 and E7. And both are incoming arrows. We write down -1 for these two. And for the rest, is 0. For E6 is -1. For E7 is -1. Let's see. For these two, we have -1. And for the rest of edges, we have 0. Because only these two edges are connected to E, and both are incoming arrows. ليه إيه ما لقى سهمك هاتو بو بوينتك بو فيرسكا ناقصك داني أجا سهمك اللي بوينتك ودرتشو بو أو يقداني أجا هيس كونكت نو إنها هاتو بندرتشو بو 0 داني هلوني والله ليه أبيت فيرسكان ليه دابني إيش كان شيء دابني فبشو داني لإنسيدنس ماتريكس. This is for directed graph. For undirected graph, we talked about this before. We talked about this yesterday. Here there is an exercise for yourselves. Now we have isomorphisms. We say, are these two graphs, G1 and G2, are the same? Here we have given these two graphs, G1 and G2. It says, are these two graphs, G1 and G2, are the same? We say, two graphs are the same. It means they are isomorphic to each other. So when we say two graphs are the same, we must prove that these two graphs are isomorphism to each other, isomorphic to each other. Okay. Now we talk about isomorphic graphs. Isomorphisms. This is the definition of isomorphism graph. We say let G to be V and E, and G prime to be V prime and E prime. Here we have two graphs. At the beginning of the chapter, we said a graph consists of two sets, which are vertices and edges. G and G prime are two different graphs. We say these are two graphs. So for G, we must have the set of edges and vertices. And for G prime also, we must have the set of edges and vertices. Here, we say G is a graph with V and E. V is the set of vertices and E is the set of edges for graph G. And for G prime, we have V prime and E prime. If we have two graphs, which are denoted by G and G prime, we say G and G prime are said to be isomorphic. For isomorphic, we must have two graphs. It's comparing two graphs, isomorphic. If there exists a pair of functions, if we have two functions, f from V to V prime, that means from the set of vertices in graph G to the set of vertices in graph G prime. And G is a function from the set of edges in graph G to the set of edges in graph G prime, such that f associates each element in V with exactly one element in V prime. That means f of each element in V, for each element in V, we must have only one image. We must have only one image in V prime. Here, let's say this is V, V1, V2, V3, let's say V4. We have these elements in V. So V prime must have the same number of elements: v1 prime, v2 prime, v3 prime, and v4 prime. It says for each element here, we must have only one image there. Let's say v1 to v1 prime, and v2, let's say to v4 prime, v3 to v3 prime, v4 to v2 prime. As you see, for each element in V, we have only one element in V prime. And conversely also. For each element in V prime, we must have only one element in V. And vice versa. G associates each element in E with exactly one element in E prime, and vice versa. It's the same for edges. For the set of edges, if we pick any element, if we pick any edge from graph G, we must have only one edge in graph G prime, and vice versa. And for each V in V and each E in E, that means for each vertex in matrix, for each vertex in graph G and each edge in graph G, if V is an endpoint of HE, so f of V must be an endpoint of G of E. This must be an endpoint of G of E. Here we talk about an example. It will be much clearer. Okay. To show that in isomorphic graphs, it must satisfy these. We say if two graphs is isomorphic, they must have the same number of vertices and edges. We must have the same number of vertices and edges in both graphs, and the same number, the same degree for corresponding vertices. That means for each vertices, for the corresponding vertices, we must have the same degree. We must have the same degree for each two corresponding vertices. And the same number of connected components. The same number of connected components. That means we must have the same number of edges. We must have the same number of edges. And the same number of loops and parallel edges. We must have the same number of loops and parallel edges. And we say both graphs are connected or both graphs are not connected. If one of the graphs is connected, so the other one must be connected also. Both must have the same property. Okay. If one of them is connected, so the other one must connect also. If one of them is not connected, the other one must not connect also. Both graphs are connected. Pairs of connected vertices must have the corresponding pair of vertices connected. If two vertices are connected in one of the graph, in the other graph, they must connect. Okay. It says, in general, it's easier to prove two graphs are not isomorphic by proving that one of the above properties fails. If there is a question to show either two graphs are isomorphic or not, if the graphs doesn't satisfy at least one of these, you don't need to follow the definition to prove it. You just need to say, since, for example, if one of them has 7 vertices and the other one has 6 vertices, you can say, since graph, let's say H has 7 vertices and graph G has 6 vertices, so these are not isomorphic. Okay? هو كبيسة المني كدو جراف ايزومورفيك نية اگر هاتو ديار بود خويا يصير جرافيك ديار يكسر راسه خوتو بري لبر أو يبون فيرتس كان يكسانية إيش كان يكسانية يعني هر خالق اللي ما نيكه هر خالق اللي ما نيكه هي أتواني أجهد يكلم صفات يعني تيانا بو يصبر لبر أو صفاته شينين ايزومورفيك نين. Okay. Now we have an example. Here it says determine whether G is isomorphic to H or not. We have these two graphs. By looking at the graphs, as you see, we have the same number of edges, the same number of vertices, okay, the same number of connected components. Then we follow the definition. We follow the definition to prove that these two graphs are isomorphic. We say both graphs are simple and have the same number of vertices and the same number of edges. In both graphs, we have the same number of vertices and the same number of edges. And all vertices of both graphs have degree 2. So we say the degree of corresponding vertices must be the same. U1 has degree 2 because two edges are connected to U1. Degree is counted, the degree of a vertex is counted by the number of connected edges to that vertex. Here for U1, we have two connected edges to U1. That's why we say the degree of U1 is 2. And V1 here is 2 also. U2 and V4, these two have the same number, the same degree. U3, V3, U2 and V2, U4 and V2. These have the same number of degree. Now we define the function. Function U, function F from U to V. U is the set of vertices in graph G. The set of vertices in graph G is U1, U2, U3, and U4. These are the vertices of graph G. U is the set of vertices in graph G. And V is the set of vertices in graph H. V1, V2, V3, and V4. You have these 4 vertices in H. Now we define the function. We define the function. We say f of U1 to be V1. F of U1 to be V1. F of U1 to be V1. Okay. And f of U3 is V3. How about f of U2? What it should be? It should be V4 because it's connected to V1. Okay? Later, alam U1 V1. Later U3 chia V3. Ay U2 chia. Come vertex connected by V1. لم قدافة but V1 أو تشي مها V3 مها V4 V3 مدانا بو U3 بو U2 تشي مها F of U2. It must be V4. It must be V4 because V4 is connected to V1. We cannot say it's V2 because it's not connected to V1. We must choose those two vertices which are connected to V1 for the image of U2 and U3 because U2 and U3 are connected to U1. So you must pick 2 vertices which are connected to V1. Okay, so here we say we define a function f from the set of vertices in graph G to the set of vertices in graph H, such that f of u1 to be v1, and f of u2 to be v4, f of u3 to be v3, and f of u4, of course, it's v2. F of u4 is v2. This is the function. We define this function. Okay. Based on this function, we are going to find the adjacency matrices for both. For both graphs, we find the adjacency matrices. If both adjacency matrices are the same, we say these two graphs are isomorphic. If the adjacency matrices are not the same, we say they are not isomorphic graphs. Yet to verify whether G and H are isomorphic, we examine the adjacency matrix AG for graph G and AH for graph H. Okay, let's write down the adjacency matrices for both. For U, for G, I mean, AG equals. The adjacency matrix depends on the vertices only. We say it's U1, U2, U3, U4. Here, U1, U2, U3, U4. Okay. How many edges are there from U1 to itself? How many edges do you have from U1 to itself? Do you have a loop? No. If there is no loops, that means there is no edge from a vertex to itself. Here, there is no an edge from U1 to itself. So we write down 0 here. U1 and U2. How many edges do we have from U1 to U2? From U1 to U2. This is U1 and this is U2. We have only one edge. We write down 1. It depends only the number of edges between the vertices. U1 and U3. We have one edge which is connected U1 and U3. Then U1, U4. We have no edges from U1 to U4. Write down 0. Then for U2. U2 to U1. U2 to U1. We have 1. We have only one edge. U2 to itself. We have no edge from U2 to itself. U2 to U3. We have no edge from U2 to U3. We write down 0. U2 to U4. We have one edge. We just count the number of edges. If there is no edge, we write down 0. If you have one edge, we write down. If you have 2 edges, we write down 2 and so. Then U3 and U1. U3 and U1. How many edges do we have from U3 to U1? U3 to U1, we have only one edge. U3 to U2, we have no edge from U3 to U2. We write down 0. U3 to U3, we have no loops at U3. That's why we say it's 0. U3 to U4 is connected by only one edge. Then U4 to U1, we have no edges from U4 to U1. We write down 0. U4 to U2, we have only one edge which connects U4 and U2. U4 and U3, we have 1. U4 and U4, we have no loops at U4. We write down 0. This is the adjacency matrix for G. Now we find the adjacency matrix for H also. Okay, but we must care about this function that we defined. If we order the vertices of G in U1, U2, U3, and U4. As you see, we order them as U1, U2, U3, U4, U1, U2, U3, U4. Then the vertices of H must be in this order: V1, V4, as you see, f of U2 is U4. Then V3 and V2. It must be in this order. It must be in this order. Okay? Since f of U1 is V1, f of U2 is V4, f of U3 is V3, f of U4 is V2. Okay? It must be in this order for the adjacency matrix of H. We say it's V1, V4, V3, V2. As you see, it must be in this order. Okay? Then for this the same: V1, V4, sorry, V3, V2. Now we find the adjacency matrix for this graph. V1 to V1. Do we have an edge which connects V1 to itself? We have no edge from V1 to itself. We have no edge from V1 to itself. We write down 0. Then V1 to V4. Do we have an edge from V1 to V4? Yes, we have. We write down 1. How many edges do you have? We have 1. Then V1 to V3, we have 1. V1 to V2, we have no edges from V1 to V2. We write down 0. Then for V4, V4 to V1, V4 is connected to V1 by 1 edge. We write down 1 here. Then V4 and V4, we have no loops at V4. We write down 0. V4 to V3, do we have an edge from V4 to V3? No, we have no edge. We write down 0. V4 to V2, we have an edge from V4 to V2. We write down 1. So the number of edges from V4 to V2 is 1. Then V3 to V1. Yes, it's connected to V1 by 1 edge. We write down 1. V3 to V4, we have no edge here. It's 0. V3 to V3, we have no loops at V3. We write down 0. V3 to V2, it's 1. Then for V2 to V1, we have no edge here. We write down 0. V2 to V4, it's 1. V2 to V3, it's 1. V2 to itself, we have no. This is the adjacency matrix for graph H. Now we compare these two matrices. If they are the same, it means these two graphs are the same. And we can say the graphs are isomorphic. Let's see. Look at the first row, second row, third row, and fourth row are the same. These two matrices are the same. That means the graphs G and H are isomorphic to each other. Okay. So to prove that two graphs are isomorphic, we just follow these steps. We first should show that both graphs have the same number of edges, the same number of vertices, and also we must show that the vertices, the corresponding vertices, have the same degree. And also we define a function. Based on this function, we find the adjacency matrix. Based on this function, we find the adjacency matrix. Okay. As for ordering the vertices, the ordering of vertices in matrix AG is this, and the ordering of the vertices in matrix AH is this one: V1, V4, V3, V2. Why? Because we define the function as this one. This is isomorphic graphs. Here, there are some examples for yourselves. Do you have any question? Now you have trails, paths, and circuits. We have some definitions. First, a walk from V to U to W, sorry, from V to W is a finite alternating sequence of adjacent vertices and edges of G. That means, let's say, if you have a graph, if you have this graph, if you want to go from A to C, if you want to go, let's say, from A to G, okay? If you want to go from A to G, is a set of sequence of adjacent vertices and edges from graph G. Let's say this is graph G, okay? From A to G, we say A to D. That means A, let's name the edges also. Let's say this is E1, this is E2, E3, E4, E5, E6, E7, E8, E9. We have this E10. We have these 10 edges. So all from A to G, we start from A. Then E9. Then D, we get D. Then we go till we get E. Yeah. We go through H, E7. Then E. Then we can get G. May someone else go through here. It's okay. Le point او point A كاروين شن vertex و H هذا بردمان هم ينسي. Le point او point A كاروين le vertex او vertex A كذا كاروين بوري رواية هر رواية بيجري نبأ. شن vertex و H هذا بردمان هم ينسي. يسليرة لأيو بوجي أجيش بيريا ليد لمرة جيوبير سرتا أيه دوا أيو أم إجي شيبو إي 9 إنجا دواتير أم فيرتكسي إنجا أم إجي إنجا فيرتكسي إنجا إجي إنجا أجابج أي كسي كليرو بيت زورا سايا A E1 B E3 C E4 F E5 G. May someone else go through here? Yeah. Okay. UG E6 hour. Abu Dhabi birimci. I'm a GPLN or KPLN from a vertex to under. Okay. We have trivial walk from V to W consists of a single vertex. That means if we have a loop from the vertex V to itself, from a loop vertex to itself, let's say V, from V to V, this is a walk. That's all from V to itself. It's all because here it's V, let's say it's E1, E1, V. It's V, E1, V. This is called trivial walk. Okay. If you have only one vertex in the walk, we say that's a trivial walk. Now we have a length of a walk. Length of a walk is the number of edges it has. For example, here, the number of edges 1, 2, 3. So we have 3 edges. So the length of this wall is 3. The length of a wall is the number of edges that you have. Okay? Here is the definition of the length of a wall. And you have trail from V to W is a walk from V to W that doesn't contain a repeated edge. Here, we must have no repeated edges. In a walk, it's possible if we have repeated edges. But here, for trail, we must have no repeated edges. As a walk without having repeated edges. It's the same as a walk, but here, we must have no repeated edges. A path from V to W is a trail from V to W that doesn't contain a repeated vertex. That means in a path, we must have both repeated edges and repeated vertices. Why? Because we say a path is a trail. If you return to the definition of trail, in trail, we said we must have no repeated edges. And it says path is a trail from V to W that doesn't contain a repeated vertex. For trail, we must have no repeated edges. And here we have no repeated vertex. So in a path, we must have no repeated vertices and edges. Okay? A closed walk is a walk that starts and ends at the same vertex. A closed walk is it is a walk that starts and ends at the same vertex. If we start from a vertex, then we return to itself. We say it's a closed walk. And you have a circuit. A circuit is a closed walk. That means we must start from a point and return to itself. We must start and return to the same point. Means starting and end point must be the same. A circuit is a closed walk, contains at least one edge. It must contain at least one edge and doesn't contain a repeated edge. We must have no repeated edges. Okay, it must be closed. That means if we start from a vertex, we must return to itself, and we must have no repeated edges. This is a circuit. For a circuit, we say it is a closed walk. It's a closed walk with at least one edge, and we must have no repeated edges. In a walk, it's possible if we have repeated edges, but in circuit, it says we must have no repeated edges. And simple circuit is a circuit that doesn't have any other repeated vertex except the first and the last. It says, say both circuit with man nabit edge دوباره حدث. علم اگر ام سکته ور بگیرم ام سکته چکاتی ابیتا simple circuit. اگر هاتو هیچ vertex دوباره جتیانم واتا bo simple circuit. In simple circuit, we must have no repeated edges and repeated vertices except the starting and end vertices, because here in a circuit we say we must start from a vertex and return to itself. That means the first and the last vertices are the same. The first and the last vertices are the same. So the only repeated vertices must be only the first and end point vertices, and we must have no repeated edges. As you see in this graph, I said this is a trail. This is a trail. Let's present the definition of trail. It says, oh, sorry. It says, it's a walk from U to V without repeating edges. We must have no repeated edges in trail, but in in a walk, it's possible if we have. Look, 1A from 1, then edge A, then 2, then B, then vertex C, 3, then C, then 4, then D, and then 2. Look, here you have a repeated vertex. It's possible if we have repeated vertex for trail. But for path, we must have neither repeated edges nor repeated vertices. Then you have E, and then 5. This is a trail. This is a trail. May someone else go from here to here or to here. It's okay. Okay. It's from a vertex to another vertex. Okay. Go through the vertices and edges. And for path, we must have no repeated edges and no repeated vertices for path. We start from here. Okay, 6 G, 5 E, 2 D, 4. From here to here is a path. It's a path. May someone else take another path. It's okay. From 7, 8, 6, this is a path. Okay, because you have no repeated edges and vertices. And then may someone else take this one. This is a path. But if you return to here, it's not a path because we get this repeated vertex. We get 2 which is repeated. Okay, so you must stop here. This is a path. For trail, we can repeat vertices, but for path, we have no repeated vertices and edges. As this is circuit, look, from 2 for circuit, let's turn to the definition. It says a circuit is a closed walk that contains at least one edge and doesn't contain a repeated edge. Doesn't contain a repeated edge. That means for circuit, we must have no repeated vertices and edges. Okay? That's it. It's for circuit. But for simple circuit, sorry, that's for simple circuit. As you see here, if we start from 2, F, this is F. We get 6. Then G, then 5, and then E, 2, D, 4, C, 3, B, 2. As you see, the only repeated vertex is 2. And we started from 2 to 0. It's okay, it's possible if you have repeated, if you have only one repeated, which is the first and end vertex. We just can have only one repeated, which is the first and end vertices. It's okay, it's still 2. Do you have any other repeated? It's two. It's okay. It's okay if you have how many times? Okay. It's okay because it's also two. We have no any other vertex which is repeated, so it's okay. This is a circuit. This is a circuit. Okay. Then for the simple circuit, we say 5G 6F E5. This is a simple circuit. Let's turn to the definition. It says, we say, a circuit is a closed wall that contains at least one edge and doesn't contain a repeated edge. But for the closed wall, in closed wall, we say it's a wall, doesn't contain repeated vertex. But here, for the simple circuit, is a circuit that doesn't have any other repeated vertex except the first and the last one. This is similar to each other because here, simple circuit is a part of circuits. Okay. For circuit, it's possible if we have repeated vertices, but for the simple circuit, we must have only the first and the last one. We must have only the first and the last one which are repeated. This and that one. We must have only these two repeated ones. Okay. As you see, this is a simple circuit. May someone else take this one? 2, 4, 2D4, C3, B2. We return to self. This is also a simple circuit because the only repeated vertex is the first and end, the starting and end vertices. Okay, let's take a break for 10 minutes. We now have Euler path and circuit. Here you have an example. It's an application example. It says the town of Königsberg, sorry. The town of Königsberg in Prussia, now is Kaliningrad in Russia, was built at a point where two branches of the Pregel River come together. It consisted of an island and some land along the river banks. These were connected by 7 bridges, as shown in the figure. Here we have this, and this. You have these 4 lands. Okay, these 4 lands. This is the river. These 4 lands are connected by 7 bridges. This is bridge 1. This is 1. This is 1. This is 1. This is 1. This is. And this. Here you have these 7 bridges and 4 lands. Okay. Here we denote the lands to be vertices and the bridge to be edges. This all land A, this all B, this is C, and this is B. Okay. If we make the graph for this, for these lands and bridges, we say this. Let's say this is C. This is C. This is A. This is B. And this is D. Okay. From C to A, as you see, from C to land A, we have only one edge. From C to A, we have only one edge. And from C to D, we have only one edge. Then from B to A, we have 2 edges. from B to A, we have 2 edges. And from B to D, we have 2 edges. Okay, we have these 2 edges. It says, is it possible to go through all the bridges without repeating going through any bridge? Yeah, if you go through this bridge to here, then to here, to here, and to here, to here, we cannot go through this one. Okay, and from if we start from any point, vertex, we cannot go through all bridges. We cannot go through all the bridges. Okay, here it's impossible to go through all the bridges. Here, these edges denotes the bridge. Okay, it's not possible to go through all the edges without repeating going through any edge. We say it's impossible to go through all of the all of these. So here we have, I really forgot to draw a bridge from C to B. Here we have a bridge from C to B. It says, is it possible to walk across all the bridges exactly once and return to the starting land area? This is the graph. This is the graph of these lands and bridges. Here we have B, A, D, and C. Here we have these 4 lands. Okay, and we have 7 bridges. We denote the bridge to be the edges and the lands to be vertices. That means here we have 4 vertices and 7 bridges. We say it's possible to walk across all the bridges exactly once and return to the starting land area. If we add 2 bridges, one from B to C, one from B to C, and one from A to D. If we add these 2 bridges, it's possible if we go through all the bridges once, exactly once, after turning to the starting line. Let's say we start from A. If we start from A, okay, we go to here. Okay, we go to there. Then we go to here. We go there. We return from this bridge to here. We go to there, then to here, and then returning to the starting point. Okay, so it's possible if we go through all the edges exactly once. If we add 2 edges, and as I said, the edges denote the bridge. That means we need to add 2 bridges, one from C to B and one from A to D, to go through all the bridges exactly once and returning to the starting point. Yeah, if we start from this point, or may someone else start from this one? May someone else start this one? It goes through here. This one. This one. This one. This one. Here. To here. To here. And then returning to it. As you see, we're returning to the same point. Okay. So for the above one, it's impossible to go through all edges exactly once after returning to the starting point. But if we add 2 edges, it's possible if we go through all the edges after returning to the starting point. Now we have Euler's circuit. We say let G be a graph. An Euler's circuit for G is a circuit that contains every vertex, every edge of G. An Euler circuit for G is a circuit that contains every vertex and every edge of G. That is, an Euler circuit for G is a sequence of adjacent vertices and edges in G that has at least one edge, starts and ends at the same vertex. Here, uses every vertex of G at least once. That means it's possible if we use a vertex more than once, but we must use at least once. Okay, so in the circuit we must have all the vertices. It's possible if we have a vertex twice or 3 times, and uses every edge of G exactly once. Here we must use each edge exactly once. We cannot use an edge twice or more. Look at this circuit. This is a circuit. Okay. Let's check if we could have an Euler circuit here or not in this graph. Look. Bo Euler circuit, we say I get the point of this speaking. The point of this speaking, the vertex sector. أبي بهمو إيجا كان أبروي. بهمو إيجا كان أبروي. تنها يكجار جي بي أي برين إيجا كان. بلام كيشانية تنجال بفرتكس كارت. أسايا. أبقرينو بوشوني خون. Okay. Here we start from this one. We start from vertex 1. 1A, 2, G, 3, F, 4, D, 5, E, 5, again 5, C. This is 2, B, then 1. We return to the same point. Okay, so this is an Euler circuit. May someone else use another way? 4D, 5E, then 5C, 2B, 1A, 2G, 3F, then 4. You're sent to the same place. Okay? There is not only one way to get the Euler circuit. Okay? It's possible if you have more than one way for getting the Euler circuit. تنها بيقرأ ناتوين Euler circuit. أتوين زيادة اللي يقرأ وكذا. So the Euler circuit is not unique. It's not unique. Okay. This is an Euler circuit because here we don't go through we don't go through any edge more than once, and we go through all the edges at exactly once. And for the vertices, it's possible if we go through a vertex more than once, but we must go through all the vertex at least once. Okay, so this is an Euler circuit. Euler trial, we have Euler trial. For Euler trial, we start from a vertex to go to another vertex. You don't need to return to the same vertex. Okay, it's the same as the above one. It's the same as this, but we start the starting and ending vertices are not the same. For the Euler circuit, the starting and end vertices must be the same, but for Euler trial, the starting and end vertices may not be the same. Here we say Euler trial from V to W is a sequence of adjacent vertices and edges that starts at V and it ends at W. But for the Euler circuit, we said starting at V and ending at V also. Pass through every vertex of G at least once. So you must go through all the vertices. All the vertices must be in the Euler circuit at least once. It's possible if you go through a vertex twice or more. And transverses every edge of G exactly once. we must go through all the edges exactly once. We cannot go through an edge twice. Look at this one here. Let's say from 2 to 4. 2B, sorry. We must contain all the vertices. Look, 1, 2, 5, E5. We must go through all the edges. Then D, 4, F, 3, B, 2. This is an Euler trial. We don't return to A. If we return to A, here we repeat this edge. So that's why we don't return to it. And for Euler trial, we say we start from a vertex and we return to another vertex. We don't need to return to the starting vertex. This is not an Euler circuit. This is not an Euler circuit, okay? Because if we start from any point, we cannot return to that point without going through all the vertices. Look, let's start from this one. If you go through here, 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 here. When you go to 1, we cannot return to 2 without going through this edge. So this edge is going to be repeated. That means here, this is not an Euler circuit, but it's an Euler trial. We can start from here to here, to here, to here, to here, then to here. This is an Euler trial. So for Euler trial, we don't need to return to the starting point, but we must go through all the vertices and all edges. We must go through all edges at exactly once, but we could go through the vertices more than once. Okay, we could go through the vertices more than once, but we must go through all the vertices at least once. لا مرجنية هل يقدر نشوف okay. Now you have theorem, Euler theorem. We say if G is a connected graph and every vertex has even degree, if all the vertices in the graph have even degree, means if the degrees are 2, 4, 8, 6, and so on. If the degree of all the vertices are even, then G has an Euler circuit. So from now, we just count the degrees of vertices. If all vertices have even degree, we say we have an Euler circuit. And for Euler trial, we say if only we have 2 odd degrees, we have only 2 odd degrees in the graph. V and W, if V and W are the only vertices having odd degree, and the rest of vertices have even degree, we say that's an Euler trial. ليرة بو Euler circuit Euler trial أتوانها degree vertex كانت دياري degree شيء degree vertex بريتيل جماري أو الجاني كبو vertex connected both vertex connected. Okay, for example, if you have A, B, let's say C, if you have these two, the degree of A is 2 because here we have only 2 edges which are connected to A. The degree of C is 3. 1, 2, 3. We have 3 edges which are connected to C. And for B, its degree is 3 because here we have 3 edges which are connected to B. we say على أجل هاتو degree كان همو يجود degree همو vertex كان جود أو أكثر رأس فوتو أمبرين أول سكت من هي أول سكت بلان بو أول trial أنا أجل هاتو start دسبيكو كوتاي أودبو أو أنا كهمو even بون همو ينجود بون تنها دسبيك وكوتاي أو دو vertex تشيبون tag بون أو أنا كأجل همو يجود بون أو أتواني بلين أول trial من هي. Okay, look, here we have an example. For this example, it says, can we have an Euler cycle or an Euler circuit from this graph? What we do, we are going to count the degree of each edge. We have each vertex, sorry, 1, 2, 3, 4, 5, 6, 7. We have 7 vertices. We write down the vertices. As you see, this 1, 2, 3, 4, 5, 6, 7. We have these vertices. Now we count the degree of each vertex. Okay, what's the vertex of? What's the degree of vertex 1? It's 2. Okay, we have 2 edges which are connected to 1, to vertex 1. So the degree of 1 is 2. How about 2? 1, 2, 3, 4. We have 4 edges which are connected to vertex 2. It's 4. Then for 3, 1, 2, 3, 4. We have 4 connected edges to 3, to vertex 3. So its degree is 4. Then for 4, 1, 2, 3, 4. We have 4 edges which are connected to 4, to vertex 4. That means degree of vertex 4 is 4. Then 5. We have only 2 edges which are connected to 5. It's 2. Its degree is 2. For 6, 1, 2. How about 7? For 7, we said we count the loops by 2. We count the loops by 2. We talked about this yesterday. This is 1, this is 2, this is 3, this is 4. That means degree of vertex 7 is 4. As you see, all the degrees are even. All are even. That means we have an Euler circuit. Yes, this graph has an Euler circuit. We can say, yes, this graph has an Euler circuit because you should write down the reason. Why do we have an Euler circuit in this graph? We said because all the vertex have even degree. These are the degrees. It's done. Okay. Therefore, this example is the same as the previous one. We just write down the degree of each vertex. For vertex 1, its degree is 2. For vertex 2, its degree 1, 2, 3, 4. For 3 is 2. For 4 is 4. For 5 is 2. For 6 is 2. All the degrees are even. That means we say this graph has an Euler circuit. You say this graph has an Euler circuit. Let's try. If we start, let's say from 2. If we start from this, we must return to vertex 2 without going any edge more than once, but we must go through all the edges and vertices. But it's possible to go through a vertex twice or more. Okay? Here. We go to here, to here, to here, to here, to here, then to here. Look, we return to this, the starting point. This Euler circuit. May someone else start from this one. Okay, you can go through here, to here, to here, to here, to here. As you see, we return to the same place. Okay, may someone else start another point. This is possible. Okay, so here we say this is an Euler circuit because all the degrees for vertices are even. Then for Euler trial, we said if only the starting and end vertices have odd degrees, and the rest of vertices have even degrees, we say that's an Euler trial. Here, look, if you could find only two vertices with odd degrees, you directly can say that is an Euler trial. ليه أقدر هادو vertex ما هبو كديجري كان odd به أقدر هادو دانيت يا أبو ديجري كodd به يكسر أتوانين بلينشيا Euler trial. Okay, let's start. Here, the degree of vertex 1 is 2. Degree of vertex 2 is 1, 2, 3. 3 is 3. 4, 2. 5, 2. 6, 2. As you see, we have only two vertices with odd degrees. That means here, this graph has an Euler trial. Let's try. We must go through all the vertices and edges. But for the vertices, it's possible if we go through a vertex twice. But we must go through all the edges at exactly once. We start from one of the odd degrees. We must start from one of the odd degrees. Okay? Here. We go through. Oh, sorry. That's it. Yeah. As I say, we start from one of the odd degrees vertex. It's possible if you go through a vertex twice or more. Look, we return to the other odd degree. We must return to the other odd degree vertex. We start one of the odd degree, we return to the other one, to the other odd degree. Look, if we start from this one, if we start from this one, from this to here, to here, to here, here. From here to here to here, and then we return to 2. We start from 3 and we return to 2. Okay, so the path here is, if you write down the path from 3, E, 6, G, 5, F, 4, D, 2, A, 1, B, 5, C, 2. As you see, we started from 3 and we returned to 2. We have only these two vertices with odd degrees. Okay. Do you have any question?